Hi guys, I hope I'm audible. So I hope everyone has the brain juice after the long series of talks today. So I'm going to talk about impact of seasonality on bistable ecosystem dynamics. So I just to uh, uh, just to go through the basics. So we all know the ecosystem can react to different changes in ecosystem conditions differently. Maybe there can be a threshold change in ecosystem states for change in various ecosystem conditions. So different ecosystems can show bistability for different ecosystem conditions, which implies a system can be two different states for similar set of ecosystem conditions. For example, here a system can exist in either forest or savanna state, depending on its prior conditions. So for such systems, there can be catastrophic shifts uh, uh, happening when the condition crosses this bistable region. And these kinds of shifts are often very drastic and catastrophic for different systems, which makes these kinds of bistable systems interesting for study. Uh, these kinds of systems can be modeled using stochastic differential equations. Suppose here the x here denotes the state variable for the system, which can be modeled using SDE with the f of x capturing the deterministic predictable dynamics in the system, and the g of x functional form, which captures the stochastic dynamics in the system. And the eta term here adds white noise to the system, which makes which adds randomness in the model. Together, this kinds of STs can be used to model systems, which are known as stochastic mean field model. So here we can model a system with different driver parameters like A, B, C, or the system can be modeled using different parameters which it depends on. But often such systems are modeled ignoring the seasonality associated with different parameters of an ecosystem. But we know that in real ecosystems, often the parameters will be prone to seasonal changes, and which makes the system to undergo seasonal dynamics. So in my study, I investigate the impact of seasonality for such drivers in bistable ecosystems. So to summarize how I add seasonality into such a mean field model, so I have modified seasonal forcing method, which has been used in a previous study by Skeffer. So I choose one of the driver of interest in the system and add seasonal forcing as a sinusoidal sinusoidal wave. And you can see here there are two parameters which can be altered in the seasonal forcing to manipulate the seasonal dynamics. One is amplitude, which denotes the extent of variations seasonality exerts in this driver parameter. And the period determines how the phase of the seasonal oscillations for the driver. So in my study, I'll be changing both this amplitude and period to study the effects of seasonal dynamics. So suppose consider a vegetation system following dynamics with a bifurcation diagram as shown here. Here the biomass density is changing in response to the driver rainfall rate. So you can see here for a fixed rainfall rate, there's a range where the system shows bistability. and the system depends on the initial condition. It depends on the initial conditions to predict which state the system is on. So the system can be either on either of the bistable states depending on its initial conditions. So you can clearly see here when I change the driver R to be seasonal, it changes the dynamics of the system, and it affects the dynamics of the time series of the biomass density. And when I alter the amplitude of the seasonal forcing, you can see it has a clear effect on the dynamics of the system. And a similar effect can be found when I change the period of the system as seasonal forcing as well, which manipulates the time it takes for each oscillation to occur. So to study this this effect, I considered first a unistable system with which has a unique a single stable state for the changing driver variable C here. So you can see the system has a single stable state for various values of this driver. And I have imposed seasonal forcing for a range of driver value from around 0.4 to 0.6, where the system resides around 0.5. And here you can see so I have considered 3 different levels of period for the manipulations. And here you can see for the levels of period which are very smaller compared to the return rate or the time scale of the system. The system resides around the stable state predicted by the bifurcation diagram shown here, and which you can see from this histogram. And the third plot denotes how the state variable is changing with respect to the oscillations in the driver. So here the as the period is very low, the fluctuations in the system are happening very rapidly. And in the next period that I considered, it is comparable to the return rate or the time scale of the system. And here you can see it has changed the patterns observed in the system. And when I further increase the period of the system, you can clearly see the system to undergo changes which tracks the corresponding changes in the driver. So in a nutshell, the seasonal forcing makes the system to have bimodality for larger periods that I considered, and a larger period makes the system to stay in equilibrium state corresponding to the driver. So which implies the system the time scale of the period and the time scale of the system has a relative has something to do with the dynamics which happens to the system. So to check if these patterns are holding true for a bistable system as well, I considered a lake model which has bistability for a certain range of the Newton loading rate, which is the driver parameter here. Similarly, I changed the driver value beyond the bistable region, so which makes the driver value to go beyond the bistability region, so which can make the system to undergo tipping points and transition. But when I consider this period to be very low and the fluctuation, the seasonal changes in the system to be very rapid compared to the system's return rate, the seasonal forcing doesn't make the system to undergo any transition, and the system resides on the stable state itself. But when I increase the period, it shows the bistability that we have observed earlier for a unistable system. And a further increase in the period of seasonality makes the system to undergo transition, as you can see here in the in this plot. You can see that the system undergoes transitions due to changes in the driver caused by seasonal forcing. So, when the yeah. So to summarize, the seasonal forcing makes the system to have bistability even when it resides on a single a single stable state, purely because of seasonal forcing, as you can see in the middle column. And for a large enough period, it makes the system to undergo transitions to different alternate states. They had considered a different bistable system, a vegetation model, which also shows similar results as we have seen for the lake model. So here also we see that bimodality for the periods comparable to the system's time scale, and for larger periods we see the system undergoing transitions. So to summarize, so the seasonality makes the system to have a spurious bimodality around the stable state for comparable time scale, period timescales to the system's recovery rate or time scale. And similarly, the seasonal forcing with large periods makes the system to respond to the changes and be closer to its equilibrium state. So when the seasonal forcing changes are very slow or the period is very large, the system actually tracks the changes in the driver and undergoes transitions at the tipping points corresponding to the bifurcation diagram you can see here. And for large enough period, the time scale required to make these transitions depends on the return time for the system. So the relative period for the seasonal forcing should be quite large enough to make such transitions occur in the system. So seasonal forcing brings in additional patterns to the dynamics of the system, which will give misleading conclusions if the seasonality were omitted in the study. Suppose if we were not considering seasonality in the system, we might falsely end up making assumptions of a bimodal system to have two stable regimes, which would be a misleading conclusion if we are not considering a seasonal forcing. So seasonality is something, seasonality in a driver is something important to look into when we are studying mean field stochastic systems. So with that, I thank everyone, and I would like to thank my advisor, Vishwesha Guttal, and all members in my lab and IISc for the funding and help. Thank you. I can take questions.
Hello. Yeah. This can you please tell me, like maybe I missed it. Which model is this? Like, what is the model?
So this is from yeah. So these are the models that I consider. So this is from originally these are from work of Guttal and Jayaprakash from 2007. So I had just modified the harvesting term to be type 3 in the vegetation model.
Okay. And in the parameter, in some of the slides, you have mentioned the time is in the years.
So that slide was just for representation, so that it doesn't
the parameterization you have considered, is it like
no, that particular slide doesn't so it's just for
in the models otherwise? how is the parameterization done?
So so for the results that I have shown, I have in parameterized. So it's yeah, so it's just in the system's time scale. So the period that I'm considering is relative to the system's time scale. It doesn't imply time in years or anything.
Can you please show the same slide where the model is described? I have a technical question. I see that your seasonal forcing is defined as equation with this eta parameter, and then it can be scaled with C, which is constant. And then if you can scroll, please, to slide number 9. My question is about amplitude in these three cases. Why amplitude of these three forcings changes so drastically? This is dictated by the model, because if you rescale them, I think histogram of at least first case would be much more clearly visible if amplitude of all the three cases was comparable. I think it would be easier to see the histograms and shape of the first one. Is it dictated by the model that the amplitude of seasonal forcing changes?
1 minute. Can you repeat the question?
So the question is on the top 3 panels on the right-hand side, the 3 amplitudes obviously change period because you compare them, but why amplitudes change so much? Amplitude, how much why they are not compared in a rescaled way? Then histograms would be much more clearly visible, especially in the first case.
I think so I have considered same length of time series for all the comparison. I think the histograms heights might be have to do with the binnings.
No, not the height. I mean amplitude in the top panels, because in one amplitude is kind of point.
Yeah. So the yeah, so the system is so the maximum changes that possible for the system based on the changes in the driver parameter is actually comes for the period 500. So the changes in the driver is large enough to make the levels of changes high comparable in the period 500. But for lower levels of periods, the system's response to the changes in the changes due to the seasonal forcing, I think the relative dynamics based on the period and the system's recovery time makes the system to fall before it reaches the potential state the system can be for that particular driver change. So for smaller periods, the system doesn't go up to the potential state change for that particular change in the driver.
Thank you.
So you showed that seasonality can bring this bimodality in the data, even though you are not undergoing tipping. So is there any way to distinguish from data the bimodality coming from this just because of seasonality and actually from transition between two between bistable states?
I think from purely looking into the time series would give some idea as if the noise in the system is not high, large enough, we can see seasonal changes in the system when we look into the time series rather than the histogram. Other than that, I think there are methods to get back an SDE followed by a system from time series data. So if we have a system which has true bistability and which shows bimodality, and a system with seasonal forcing which shows bimodality can be distinguished using such a method. So suppose if we compute the first and second gem moments of a time series from arising from a system with SD following an SD, we can actually get back the model followed by the system if the system is actually non-seasonal, and such a computation won't be possible for a seasonal system. So that could be one way to distinguish, I think.
You have given seasonality perturbation in one parameter or all parameter?
A particular parameter, the driver,
yeah, in one parameter. That means you have after giving this perturbation, you have calculated this value. Means if a equal to a into 1 minus 2 pi cos of 2 pi by t into t, that means I can easily calculate one column for this value of this driver.
So I'm not giving the driver is keep on changing over time in the system. So during my simulations, the driver will be changing as a function of time throughout the time.
But when you are plotting with driver,
Yeah.
then you are taking one fixed value, na?
No. I'm plotting the corresponding driver for the corresponding value of the state variable for that particular instant. Yeah.
Okay.